Hey, what's up, everybody? I hope you're enjoying your spring break. And what I've done here today, or what I'm going to do today, is give you a little bit of bonus 2302 content on protecting groups, which is where we ended our class on the Friday before spring break. There were definitely some questions about this in the Muddiest Point post-class survey. So I thought that we could go over this in a little bit of a bonus video, set you guys up better for your exam, which is coming up the Wednesday after spring break. So what I'm going to do today is go through a few examples where protecting groups are necessary in order to accomplish a multi-step synthesis problem. So why don't we get right into it, and we'll draw a potential multi-step synthesis problem and talk about both why and how we would use a protecting group to solve it. So let's get started with this one here. I'm going to draw a molecule that you might see as a starting material for a multi-step synthesis problem. So here's a bromide. We're also given an epoxide as starting materials. And the question would be, how would we accomplish a synthesis of a molecule for the target that would look like so? Okay, let's make sure I'm counting this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, so this would be a potential problem like you might see on an exam situation. And the first thing that I notice here is that we have an epoxide starting material and a halide, and that we need to make a carbon-carbon bond. If we count our carbons like so, I can map those 5 carbons onto the product. And now I can see that these 3 other carbons are likely going to be the ones that I'm going to want to bring in from the other epoxide reagent. We've seen carbon-carbon bond forming reactions with epoxides in the past, and we know that the way that we would like to do this is through the intermediacy of an organometallic intermediate. And that would open up our epoxide the right way. So ideally what we would want would be something that would look like this. Let's say we wanted to convert that bromide into a Grignard reagent. That might be our ideal reagent for accomplishing this synthesis. If we think about this mechanistically, so a little bit of review. If we were able to use this ideal reagent, we could use the curved arrow formalism and show how we would attack the less substituted side of the epoxide. That would generate an alkoxide. Oops. Quick correction there on the iPad. That would give us an alkoxide like this. Magnesium bromide would be our counter ion. And then we would use hydronium to work this up and get the target molecule. However, the problem with this synthesis is that even though these curved arrows look fine, this synthesis will fail, because this ideal reagent would never live long enough to actually interact with the epoxide. Remember, we would typically try to make that sort of thing by treating the bromide up above in the upper left hand of my slide with magnesium in a solvent like THF or ether. And only in a second step will we be adding the epoxide electrophile. So that means that this thing would have to live with itself for a decent amount of time before the epoxide would actually show up. So let's talk about what would happen if we tried to do that. So let's just say that we had this Grignard reagent. We had formed that. I'll redraw it here. Suggestively, drawing out one of those OH bonds. If we actually had formed this compound, Well, Grignard reagents are not that stable to things like water or alcohols. So what would happen instead, again showing you this with the curved arrow formalism, is that we do a deprotonation reaction of this alcohol. Now this could take place internally, as I'm showing here, or we could even imagine a second molecule of the Grignard reagent coming around to serve as an acid to deprotonate the alcohol and quench that Grignard reagent. Notice that this doesn't need to have the epoxide around, so this sort of reaction would take place before the epoxide even got into the reaction mixture. Okay, and now we've just transferred that hydrogen over here and we have the alkane. So this means our proposed synthesis that we drew out on the last slide would fail. So what's the solution to this? One way to make this work would be to try to use a protecting group to protect this bisphenol diol in our starting material and allow us to form the Grignard reagent, protecting it as a functional group that wouldn't otherwise react with Grignard reagents. And as we discussed over the last week of class, the Acetal functional group or the Ketal functional group, both of them react way more like ethers than either the alcohols or carbonyl compounds that they're made from. So we're going to use that in order to solve this multi-step synthesis problem. Here would be a potential solution. Let's start with that bromide that we had back on the first page. What we could do is react that with a ketone that would tie up the diol into an acetal. Let's use a ketone like acetone. So I would draw out the structure of that ketone. I would draw an acid catalyst like tosic acid, and we would do this in a solvent like benzene and heat, removing the water in order to drive this all the way to the Ketal product. Now I have my bromide. What I can do with this now is generate the Grignard. So I might use conditions like magnesium in diethyl ether. Then we react it with the epoxide starting material. And then finally we use hydronium to quench that alkoxide product from the Grignard, attacking the epoxide. So we have hydronium. This would then almost get us all the way to the product. You can see that the ketal is still present in the molecule. And I have the secondary alcohol I expect from the epoxide opening reaction. What I do now is I run the ketal synthesis in reverse. Again, we're going to use Le Chatelier's principle here, except now we added in an excess of water. We'll keep the same acid catalyst, tosic acid, and this would allow us to free up that diol, regenerate acetone as our byproduct, and give us the alcohol product that we desired as our final product. So instead of just being able to do this directly from the bromide, using the Grignard reagent, we use the protecting group in order to get all the functional groups that we know are compatible with Grignard reagents into that intermediate before we make the Grignard. Okay, so that's one way of doing it. What I'd like to do now is talk about another problem. I'm going to set this one up so that what I'd like you to do is think about how you might use protecting groups for this problem if you were doing it on your own. So we'll start off with something a little bit different. Now we're going to have two functional groups in our molecule, carboxylic acid and a ketone, and they'll be connected by this benzene ring. What I want you to think about doing is how could we convert this compound to where the ketone is still present in the molecule, but the carboxylic acid has been reduced to the primary alcohol. So if you're following along on your video, maybe at this point, after I get in those final double bonds, you can hit pause and then think about how you'd try to accomplish this synthesis if you were working it on your own. Okay, have you had a chance to think about it? Let's first talk about why we might need to use a protecting group in this case. Let's think about what would happen if we tried to reduce the carboxylic acid to the primary alcohol on its own without using it. We might remember that the reagent that we need in order to reduce a carboxylic acid to a primary alcohol is lithium aluminum hydride. So let's try to draw that out. The question is, would this work? If I treated this with lithium aluminum hydride and then reacted it with water, certainly the carboxylic acid would be reduced to the primary alcohol. But that's not all that would take place. Remember, lithium aluminum hydride is our strongest reducing agent, and it reduces all the carbonyl groups that we've talked about in the past. So we wouldn't get this as the expected product. Instead, we'd get a product that would look like this, where this ketone has been reduced to a secondary alcohol as well. Now, maybe some of you were thinking about how you might try to resurrect this synthesis by converting this diol into the product up above. And every time you're contemplating that, just ask yourself whether or not you have a reagent for accomplishing that transformation. We have learned lots of different oxidants that can convert secondary alcohols into ketones. But it turns out all of those oxidants that we've learned about also convert primary alcohols into either aldehydes or carboxylic acids. And we haven't learned a way that only works with secondary alcohols to ketones without doing primary alcohols. So we don't have any reagents that can do this. So there's no reagent we know. So how to solve this problem? The theme of the day is protecting groups, so let's see how a protecting group could be used to solve this problem. If I start out with that ketone, and the carboxylic acid, I could do a protecting group, a Ketal formation reaction with the ketone in my starting material, and it should leave the carboxylic acid relatively free. So if I look at this, I could start out with a diol. I could also use a regular alcohol like methanol if I wanted to. We have several options. Again, treating it with tosic acid, benzene, and heat. Drive this to the formation of the ketal. And we'd have the carboxylic acid. Now at this point, we could use lithium aluminum hydride. Lithium aluminum hydride does not react with ethers. It also doesn't react with ketals or acetals. It would reduce the carboxylic acid all the way down to the primary alcohol, though. So that would give us our primary alcohol that we need in our product, leaving us the ketal on what I'm drawing as the top half of the molecule. Now, to free up that ketone that we want in our final product, we would then, again, run the reaction with acid in reverse. So we would add a bunch of water and tosic acid. That would free up the ketone and leave us with the primary alcohol in the position we wanted. The byproduct here would be diol, but this would be sufficient for a full credit answer in an exam type situation. All right, are we ready to try just one more? Okay, let's think about another multi-step synthesis problem. I'm going to draw a structure with a triple bond in it. And on the other side of this benzene ring, I'm going to have an aldehyde. Our other reagent that we'll use, our reactant for our multi-step synthesis, will be another aldehyde. The goal, where we want to get to at the end of the day, is going to be a compound that looks like this. I have the benzene ring in the middle, a carbon-carbon triple bond, and then it'll be connected to a secondary alcohol. But we want this aldehyde on the other side of the benzene ring to stay put and still be there. So what I'd like you to think about now is what type of reagent would we actually want in order to accomplish the formation of this carbon-carbon bond in the product right here, and think about why we're going to have to use a protecting group in order to accomplish this synthesis using the reactions that we've talked about in class so far. So what I'd like you to do is draw out the organometallic that we need and then think about what the problems are with that organometallic. So hit pause and draw that out right now. Okay, you had a chance to think about it? Let's draw out that reagent together now. I'll draw it out and you can compare it to what you've drawn at home. Okay, I would want an organometallic right at this carbon right here that would allow me to attack acetaldehyde and form the carbon-carbon bond that I need in my final product. So what that would look like would be the benzene ring with the triple bond, aldehyde on the other side, ideally, and then it might look something like this. I might have chosen to use an organosodium. You might have drawn out a Grignard. That would also be correct. But the problems embedded in this ideal reagent, are still apparent. If I form an organometallic that looks like this, I'm going to have a reactive functional group on the other side of the molecule, right here in the aldehyde. So let's imagine what would happen if I took this aldehyde and then tried to form the organometallic on that triple bond. So I would have a solution that would have a bunch of this organometallic in it, so a whole bunch of molecules right next to each other. And in fact, another one could look just like this. It could saddle up beside another molecule of itself. If we want to give our reagents some anthropomorphic characters, we'd say, I've got a strong nucleophile on this side that would really like to react with the electrophile on the other side of the molecule. So one of these could just find its neighbor, attack the aldehyde, and then all of a sudden we don't have the organometallic that we need anymore, and we don't have the aldehyde that we want in our final product either. We'd have products that would start looking kind of complicated. Might start looking something like this. My mistake on the hydrogen there. This should be an alkoxide. And we can see that this could even keep going. I've still got an organometallic on one side, aldehyde on the other side. It could maybe start finding even more molecules of the starting organometallic to react with. So this isn't going to be a successful synthesis. So how can we use a protecting group to solve this problem? Well, we start with that aldehyde, and I think the theme of our little bonus lecture here so far is using an acetal or ketal protecting group to protect this functionality from the reagents that we want to use. So in this case, what we would do is form an acetal. In this case, I'm going to draw this one out with methanol. We use excess to drive the equilibrium for the acetal all the way to products. You could use the diol like we used in the last problem. You could use ethanol instead of methanol. There are a whole bunch of different correct ways to do this portion of the synthesis. Okay, now you have an acetal that would be stable to those organometallic reagents that we want to use in the next step. So in order to do that, let's generate that organosodium that I talked about that we might like to form. Remember that the reagent for doing that is to use sodium amide, Na, NH2, in a solvent like diethyl ether. Now we can use the aldehyde that we needed to solve our multi-step synthesis problem, that other given starting material, acetaldehyde. And finally, we add a proton to generate the secondary alcohol that we need, and that is typically just done with hydronium. So that would get me to an intermediate where I still have my acetal, but I've been able to form the carbon-carbon bond that we needed to form in order to get us closer to the final product. Now we run the acetal formation in reverse. I take this structure, treat it with excess water. Again, we'll use tosic acid. And we can get the aldehyde back. While still having the secondary alcohol that was required by the problem. So we've made our target molecule. What you can do on your own now is go through and look at the different lists of reagents that we came up with back on last Friday that were all either incompatible with aldehydes, ketones, or alcohols, but compatible with things like ethers, acetals, and ketals, and think of other ways that you could use protecting groups in multi-step sequences. There are also some great problems at the end of chapter 18 in your textbook under the synthesis heading, where you can also practice these types of skills. We'll be picking up here on Monday, getting ready to review for exam 2, which is again coming up on Wednesday. I hope you all are enjoying the rest of your spring break, and thanks for spending a little bit of time with me reviewing these concepts. See you on Monday. Bye-bye.